Good afternoon to all of you. First of all, I want to introduce myself Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering, and today my content is GTU question paper solution of the subject of vector calculus and linear algebra of January 2013. So up to question number 5a we already seen this question paper. So let's see question number 5b. Find the associated matrix of the linear transformation T from R3 to R3, where T of x1, x2, x3 is equal to x1 plus x2, x2 plus x3, x3 plus x1, with the basis B is equal to 1 0 0, 1 1 0, 1 1 1, and B dash is equal to 1 0 1, 0 1 0, 1 0 minus 1 for the domain and codomain respectively. This question was asked in 3 marks in this question paper. Here B and B dash both are bases for R3, right? Our transformation T from R3 to R3, and we have two bases. One basis is for domain and another basis is for codomain. Now what is the question? Just try to understand first of all question. Find the associated matrix of the linear transformation T, where T is already defined, where T of x1, x2, x3 that is equal to x1 plus x2, x2 plus x3 and x3 plus x1. Now first of all we have to find all the images corresponding to the elements of the basis B, right? So T of 1 0 0 we have to find T of 1 0 0, T of 1 1 0, T of 1 1 1. Okay, so images of these three basis vectors, that is also vector of R3, right? That is also vector of codomain, and we have already the basis for the codomain. So that all the images can be expressed as linear combination of these three basis vectors, of B dash, right? And whatever we get the coefficients, that is our requirement scalars, right? So let's try to find out all the scalars, and let's try to solve this question. Here T of u1, u2, u3 that is equal to u1 plus u2. Instead of x1, x2, x3, here we are using u1, u2, u3. Okay, so u1 plus u2, u2 plus u3, u3 plus u1. T of 1 0 0 that is equal to 1 0 1. T of 1 0 0 that is equal to, you can see, instead of x1, x2, instead of u1, u2, u3, we will put 1 0 0. So finally you will get T of 1 0 0 that is equal to 1 0 1. Then T of 1 1 0, instead of u1, u2, u3, we put 1 1 0 respectively in this definition. So you will get easily 2 1 1, and T of 1 1 1 that is equal to, you can see, 1 plus 1 2. This is also 1 plus 1 2. This is also 1 plus 1 2. So T of 1 1 1 that is equal to 2 2 2. Now let T of 1 0 0 that is equal to A into 1 0 1 plus B into 0 1 0 plus C into 1 0 1. Now these three are basis vectors of B dash. You can see 1 0 1, 0 1 0, 1 0 minus 1. So T of 1 0 0 that is equal to A into 1 0 1 plus B into 0 1 0 plus C into 1 0 minus 1. So 1 0 1 that is equal to A plus C, then B, then A minus C. Okay, now comparing the left hand side part and right hand side part, we will get A plus C is equal to 1, B equal to 0, and A minus C is equal to 1. Okay, so equating the corresponding coefficients, we get A plus C is equal to 1, B is equal to 0, and A minus C is equal to 1. Now solving these equations, we get A is equal to 1 and C is equal to 0. Okay, A is equal to 1 and C is equal to 0. Solving, when we solve these two equations, A plus C is 1, A minus C is 1. When we add these two equations, we get 2A is equal to 2. So A is equal to 1, and when we put the value of A in one of the equation, we get C is equal to 0, right? So 100. Here is the answer 100. Similarly, we can find, you can see this is 101. This is, we find T of 100, and that T of 100 can be expressed as linear combination of element of B dash, right? Now similarly, we can also find the scalars such that that scalar using in the linear combination of the basis vector of this B dash, and that can be expressed as T of 110, right? So that means what, T of 110, that is also can be expressed as linear combination of these three elements, right? 1 0 1 0 1 0 and 1 0 minus 1. So we find T of 110, that can be expressed as linear combination of basis elements of B dash, 1 0 1 0 1 0 1 0 minus 1, right? So T of 110, that can be expressed as A into 101 plus B into 010 plus C into 10 minus 1. So, and T of 110, we have already 211, that is equal to A plus C, B, A minus C. This right hand side part is common in all the solving the images of the linear combination. So A plus C is equal to 2, B equal to 1 and A minus C is equal to 1. So B is equal to 1, A plus C is equal to 2 and A minus C is equal to 1. Solving these equations, we obtain B is already 1. When we solve these two equations, A plus C is equal to 2 and A minus C is equal to 1. When we add these two equations, we get 2A is equal to 3. So A is equal to 3 by 2, and put the value of A in one of the equations, we get, you can see, put the value of A is here 3 by 2. So C is equal to 2 minus 3 by 2. So that will become C is equal to 1 by 2. Okay. Now again similarly we can find T of 111, that can be also expressed as linear combination of element of B dash. So T of 111, that is equal to A into 101 plus B into 010 plus C into 10 minus 1. So 2 2 2, that is equal to A plus C, B, A minus C, right? So A plus C is equal to 2, B is equal to 2 and A minus C is equal to 2. Solving these equations, we obtain definitely B is equal to 2. When we add these two equations, 2A is equal to 4, right? When we add these two equations, we get 2A is equal to 4. So A is equal to 2, and put the value of A is equal to 2 in one of this equation, you will get C is equal to 0, right? So here is a associated elements T of 100 respective to the basis B dash, that is equal to 100. You can see what is our value of ABC. In the first solve these equations, 100, right? Then T of 110, when we write down T of 110 as a linear combination of element of B dash, what will we get? ABC, the value of ABC, that is equal to 3 by 2 1 1 by 2, right? So here 3 by 2, here is a mistake, this is 3 by 2 1 1 by 2, and then you can see the value of ABC when we write down T of 111 as a linear combination of element of B dash. In that case we get the value of ABC, that is 220. So here 220, right? Now this is our first column of the matrix, this is our second column of the matrix, and this is our third column of the matrix. So this is T100, right? Then 3 by 2 1 1 by 2, right? 3 by 2 1 1 by 2, and this is 220. So this is our associated matrix which is required to solve this example. So here to complete the solution of this question, next question, question 5C. First part, show that the transformation T from R3 to R3, show that the transformation T from R3 to R3 defined t of x1 x2 x3, that is equal to x1 minus x2 plus x3, 3x1 plus x2 minus x3, 2x1 plus 2x2 plus x3. Is it linear or not? That is the question, right? To prove that any transformation is linear or not, there are two conditions which we have to prove. T of x plus y, that is equal to t of x plus t of y, and the second condition is t of alpha into x, where alpha is any scalar. T of alpha into x, that is equal to alpha into t of x. If we combine these two conditions to become a linear transformation, then we get only one condition, t of alpha x plus beta y, that is equal to alpha t of x plus beta t of y. If we prove the only this one condition, then we can prove that our transformation is linear. So to check that this example, in this example our transformation is linear or not, we are trying to prove that t of alpha x plus beta y, that is equal to alpha into t of x plus beta into t of y. So here is two vectors x and y. X is equal to x1 x2 x3, y is equal to y1 y2 y3 belongs to R3, and alpha beta belongs to R. T of x is equal to, just we are using the definition, t of x1 x2 x3, that is equal to x1 minus x2 plus x3, then 3x1 plus x2 minus x3, then 2x1 plus 2x2 plus x3. T of y, that is equal to t of y1 y2 y3, that is equal to y1 minus y2 plus y3, then 3y1 plus y2 minus y3, and 2y1 plus 2y2 plus y3. So now t of alpha x plus beta y, now we are trying to prove t of alpha x plus beta y, that is equal to alpha t of x plus beta t of y. So t of alpha x plus beta y, that is equal to t of alpha x1 x2 x3 plus beta y1 y2 y3. So that is equal to t of alpha x1 plus beta y1, alpha x1 plus beta y1, that is our first coordinate, then alpha x2 plus beta y2, that is second coordinate, and then alpha x3 plus beta y3, that is our third coordinate. So just first of all try to understand our definition of the transformation t of x1 x2 x3. So this x1 x2 x3 are actually the first, second and third coordinate, right? And corresponding to that first, second, third coordinate, here we are using this definition. This x1 minus x2 plus x3 means what? This is first coordinate minus second coordinate plus third coordinate. Similarly, this 3x1 plus x2 minus x3 means what? This is 3 into first coordinate plus second coordinate minus third coordinate, right? So using that way, when we are applying our definition of this transformation, applying on these three coordinates, first, second and third coordinates, then we get first coordinate minus second coordinate plus third coordinate. So definitely we get, this is first coordinate alpha x1 plus beta y1, you can see, minus second coordinate minus alpha x2 minus beta y2, right? And then plus third coordinate alpha x3 plus beta y3. So similarly 3 into first coordinate plus second coordinate minus third coordinate. So 3 into first coordinate, that is alpha x1 plus 3 into alpha x1 plus beta y1. So 3 alpha x1 plus 3 beta y1, then plus second coordinate, so that is alpha x2 plus beta y2, alpha x2 plus beta y2, minus third coordinate, so that is minus alpha x3 minus beta y3, and then this is 2 into first coordinate plus 2 into second coordinate plus third coordinate. So we get 2 into first coordinate, so that is 2 into alpha x1 plus beta y1, so that is 2 alpha x1 plus 2 beta y1, plus 2 into second coordinate, so that is 2 alpha x2 plus 2 beta y2, and plus third coordinate, so plus alpha x3 plus beta y3. Now you can see alpha x1 minus alpha x2 plus alpha x3, right? We have written first all the terms of alpha, So you can see alpha x1 minus alpha x2 plus alpha x3, then in second coordinate 3 alpha x1 plus alpha x2 minus alpha x3, and then in third coordinate when we together all the terms of the alpha, then you will get 2 alpha x1 plus 2 alpha x2 plus alpha x3, right? So similarly plus in the second term we are writing all the terms of beta, that is beta y1 minus beta y2 plus beta y3, that is our first coordinate of the second term. Then the second coordinate is 3 beta y1 plus beta y2 minus beta y3, and then 2 beta y1 plus 2 beta y2 minus plus beta y3. So then alpha will be common from the first term, so alpha into x1 minus x2 plus x3, then 3x1 plus x2 minus x3, and then 2x1 plus 2x2 plus x3 plus beta into y1 minus y2 plus y3, 3y1 plus y2 minus y3, and then 2y1 plus 2y2 plus y3. So this first term is exactly alpha into t of x, the definition of t of x, right? The definition of transformation. And similarly this is t of y. So you will get alpha into t of x plus beta into t of y. So we are starting with t of alpha x plus beta y, and that is equal to, we prove that alpha into t of x plus beta into t of y. So t is linear, right, using this proof. Another way to check that our transformation is linear or not, that is one another method. In that method you can directly check that our linear or your transformation is linear or not. Just you have to write down your argument in words. You can see our coordinates, this is t of x1 x2 x3, right? If all the coordinates of the definition, that means x1 minus x2 plus x3, this is first coordinate, this is second coordinate, this is third coordinate, you can see all the coordinates are linear. Linear means what? That can be expressed as linear combination of x1 x2 x3, right? All the coordinates, either you say w1 is equal to x1 minus x2 plus x3, so that is also linear, w1 is linear. Say w2 is equal to 3x1 plus x2